Hi, my name is Ravi Syaputra. I'm a student in Syaputra University, majoring in Mechanical Engineering cohort 2022. So for today, I'm going to be discussing about the three strengthening mechanisms for metal materials. Okay, so we're moving on to the table of content. Today, I'm going to be discussing three strengthening mechanisms as promised. So first of them is strengthening by grain size reduction, strength hardening, and solid solution strengthening. The first method that I'm going to be explaining is the strengthening mechanism by grain size reduction. So the first concept that is required to be known is that when a slip plane encounters with a grain boundary inside of a material, that slip plane is forced to be shifted perpendicular to the grain boundary. This shift in slip plane forces the dislocation to change in direction, therefore making materials not easy to slip or fracture in one way. So instead of making a slip plane that its direction is just a straight line all across the material, we create more grain boundaries by reducing the grain size so that the slip plane is continuous from grain 1 to another grain, therefore making it harder for materials to dislocate or slip. So by knowing that concept, we need the material's grain to be smaller in size, therefore resulting in more grain boundaries, which can increase the material strength by further restricting the dislocation motion. So the strengthening mechanism by grain reduction is supported by the half-page equation, which states that sigma y equals sigma o plus ky times d to the power of minus half, where sigma y is the yield strength of the material, sigma o is the lattice resistance rest of the material, ky is the half-page slope, and d is the average grain diameter inside of the material. So the half-page equation explains the inverse relationship between the diameter of the grain size of a material with the yield strength of the material itself. As the grain size of the material decreases, the yield strength of the material increases, as can be seen from the graph on the left. The second strengthening mechanism that is going to be discussed today is the solid solution hardening. It is a technique to strengthen and harden metals by adding alloying atoms to a metal to enhance its strength and hardness. This occurs when the solid atoms dissolve in the metal's crystal lattice, which leads to a distortion of the lattice structure. So there are two types of alloying methods, which are substitutional alloys, which is formed when atoms of similar size replace each other in the crystal lattice, and second is the interstitial alloys, formed when a smaller atom fit into spaces between larger atoms in the crystal lattice. So how that exactly work? How can alloying impurities into our metal actually hardening our material? So solid solution hardening actually enhances the material strength by introducing solid atoms into a material's crystal lattice, which then creates a local distortion. These distortions can avoid dislocation motion, which making it more difficult for dislocations to move through the crystal structure, therefore increasing the material's overall strength. So for example, by adding 30% of zinc atoms to copper materials, we can create brass. This is called as the substitutional alloys, because zinc atoms, being a larger molecule, disrupts the direction of the slip plane or the dislocation line, as can be seen from the picture. So this distortion making it harder for materials to be fractured, therefore increasing the material's yield strength itself. So the last strengthening mechanism that we're going to be discussing today is the strength hardening. So strength hardening is a phenomenon by which a ductile metal becomes harder and stronger as it is being plastically deformed. Strain hardening is also called as cold working because the deformation of a material takes place in a relatively cold temperature relative to the absolute melting point of the metal. So we can actually calculate the percentage of cold working that has been done to a material by a rather basic percentage formula, which is percent cold working equals to the original area minus area after deformation over original area times 100%. So when a metal undergoes cold working, the process significantly increases the dislocation density within the material's crystal structure. This higher dislocation density creates an additional obstacle for dislocation to move, therefore leading to a strain hardening. As the material is deformed, dislocations become entangled and interact with one another, further impeding their movement and increasing the overall yield strength of the material. In addition, cold working also distorts the grains of the metal. The grains tend to elongate in the direction of the deformation, which alters their shape without significantly changing their size. This elongation affects the material's mechanical properties. Also, the process often leads to a reduction in the cross-sectional area of the material, which can enhance its strength but also affect its ductility in exchange. The three graphs below showing the rate of which cold work can increase the tensile strength of a material but also decrease the ductility of a material. For the first graph, notice that there is a significant increase in tensile strength for about 100 until 200 MPa for the materials of 1040 steel, brass and copper. So accordingly to the percentage of the cold work being done by the material, we can increase the strength of metals by much. However, can be noticed that for materials like steel, a cold work more than 50% is the maximum capacity before the material fracture due to the plastic deformation caused by the cold working. The right-hand side graphs showing that the ductility of materials such as brass, steel, and copper being greatly reduced as a side effect of the cold working procedure. As can be seen, the original ductility of the three materials, which are below 25% of their original length, being greatly reduced to just around 5% elongation of their original length. Therefore, engineers must be careful to use strain hardening as a method to strengthen their materials, because it can make their materials very brittle, which is dangerous for engineering application as it can cause fracture rapidly as compared to ductile materials. Additionally, the graph on the far right showing the stress versus strain graph of a material which is a carbon steel, which has a varying cold work percentage being done on them. Notice the significant linear proportionality between the 0% cold work carbon steel and the 4% and the 24% cold work carbon steel, showing that cold working can greatly affect the yield strength of a material. However, when being compared about the strain rate of the carbon steel, which has 0% cold work on it, comparing with 24% cold work, it can be seen that the side effect of the strain hardening can make the material fracture much faster, therefore making it less ductile. So below are the two of many processes that can be done in order to achieve strain hardening. The first method is the cold rolling method, which is a metal forming process where metal stock is passed through the rollers below its recrystallization temperature, which is done to reduce the thickness of the material and increase length, also create a new grain structure which can harden the material. The second method is called as cold extrusion, which reshapes metal by forcing it through dies using compressive force below its recrystallization temperature. This method also reduces the thickness of the materials in order to harden the materials and therefore increase the yield strength of the material. So here are the sources that I used to make the graph. And thank you. Have a good one.